for this, we're going to have ranged units that fire instantaneously, that have the same range and cover no volume. Because if we put in any of those columns, if we put in any of those variables, our problem gets complicated beyond belief. So we'll have a population for region N1, and then we have a second population for region 2. Okay. In this population, after a single volley hits, after volley 1, N1 will obviously deal N1 times D, where D is the amount of damage it can do, and N2 will deal N2 damage times D. Now the similarity stops here, because let's assume for a while that N1 is microed perfectly, and N2 is microed in the worst possible way. Okay? So how do you remember what perfect micro is? All right, what's perfect micro? Exactly. You shoot the most number of weapons for the longest period of time. So that includes, so conversely, that means killing as much of N2 as possible, while N2 is not killing N1 at all. So for reality's sake, let's say N2's damage is being evenly spread out through all of N1, so not a single unit dies, but N1 fires in such a way that it's concentrated on N2 units. So after each volley, we're going to have some number of deaths. So it's going to be, so let's N2, who suffered perfect micro, will have N2 minus N1 times D over HP. So we'll have, so this is the number of units still alive, while over here N1, we still have N1 units alive, because N2 had one worse possible micro and didn't kill a thing. So you can see the difference starts to happen for volley 2. Again, we're using the same exact units, because with the same exact units, we have the least number of other factors like, oh, N1 won't reload in time, or let's suppose dragoons have a longer range. So we won't deal with any of that and assume they're all in the same space. Okay? So N1, again, will deal N1 times D damage, and N2, this time, will deal N2 minus N1 times D divided by HP times D damage. So just in case any of you get confused, N1 is going to be population 1. N2 is going to be population 2. D is the amount of damage per marine, or whatever units. We're using marines because they fire instantly. And HP is the HP per unit. So you can see this is what happens. And then, so obviously for after volley 2, N1 is still going to have N1 units, while this time N2 has N2 minus N1 times D divided by HP, minus again N1 times D divided by HP, because again, this is how many units N1 has killed. So if we do this after M volleys, we'll end up with the following. We'll have out of population N1, N1 will all survive. And after N volleys, we'll have N1 times D times M. Okay? And out of N2, N2 minus M times N1 times D over HP will be still alive. And how much damage? Well, if you do the summation, we'll have N2 times M minus the sum of M equals 1 up to N, like variables. From I equals 1, it's just the sum of I N1D over HP. If you don't know sums or never done them or don't remember, don't worry because I'm going to give you the results. So this will end up to be damage dealt equals N2 M minus I times M times M plus 1 times N1 D over HP. I'm going to assume you guys know what HP is and erase some of this stuff so you don't get confused. D. So this is the amount of damage after M volume, okay? This isn't especially significant because like most imperfect micro possible is very difficult to achieve, and most perfect micro possible is also very difficult to achieve. So it won't be so it won't be a real life application. However, the importance of this is that you can see what order of growth you have. For instance, here we have N1 dm, okay, and the modification here is N2 m minus m plus 1 N1 d over HP. This is of the order m squared. That is what's really important. So we now have a calculation that shows that with perfect micro, the number of units that you can preserve grows with the number of volleys times squared. Okay. We'll see in future calculations. I mean, you have no basis like for comparison yet. We'll see in future calculations. We'll see some things like macro. If you apply perfect macro, for instance, your income will grow with e to the x. For some other things, like keeping your army together, which we'll discuss later on today, your growth or change between most perfect and most imperfect will grow with it's called cosine, hyperbolic cosine of a function. But the basic thing is you get to see the order at which the difference between most perfect and least perfect micro is. However, you are all curious people, I'm sure, and you want to make this better, okay? So you're not satisfied with the fact that we can only calculate the difference between perfect. We can only calculate it for discrete quantized volleys. So because there's got to be more to Starcraft than that. So we can use more generalizations to figure out more. Do you guys want this up, or can I move this board up to make it easier to see? You guys want to see this go up? Yeah? Okay. So this is what's important. Just remember it's in the second order. This is what I like to call population dynamics. Okay? Because it's dynamics, or how a population changes through time. So what we have here is we have, let's say, a population A and a population B. Okay? These are just any random population, a population of units, another second population of units. Now, what is the depth of A dependent on? Well, it's dependent on B, right? It depends on how much B fires. So we're going to assume that there exists some rate, alpha, at which A dies, but alpha, the death rate, is dependent on B. Conversely, beta times A is the rate at which A dies. Very logical, right? This population of A is the rate at which it dies. The rate at which it dies is dependent on the second population. The second population, conversely, is dependent on the first population. Okay. So, how much of A do we have left after time t? Well, A of t, are you guys all familiar with this notation, A of t? So basically the population A as a function of t. So how much A is left after some time t? Equals A naught, which is the initial population, minus the integral of alpha b dt. Okay? Alpha b dt is simply how much of b is left. How much of b is left, multiply the rate, and multiply all by time. So if we have, let's say, population of b goes like this, let's say. Let's just assume that's how the population of b goes. How much of A dies is just the area under B. Whereas most of you said these beds are calculus, so I'm assuming you know that. So, after this, but what is B? Well, we can write B as a similar equation. B equals B naught minus integral of beta times A dt. So now that we have a formula for B, we can substitute it back into A. A of t is A naught minus integral of alpha times b, alpha times b naught minus integral of beta times alpha dt. And this equals A naught minus integral of alpha b naught dt plus integral of alpha beta a dt, second integral dt dt. Okay. This equals A naught minus alpha b naught t plus second integral of alpha beta a dt dt. Okay. I sort of rushed through the derivation of that, but the more important thing is to listen to what's coming up next, which is why we need to know this. Okay. A naught. What is A naught? Guys, what is A naught? Initial population. Initial A, right? What is B naught? Initial B, right? So, if we weren't taking calculus or differential equations or anything into effect, all we have is this term, A minus alpha beta naught times T, which is essentially saying, what's your initial population, multiply by, subtract how much of B kills in T time. So it's very simple. This is essentially what we had before. Now the complicated thing is the second integral of alpha beta A, which is actually not just A, but A of T, dt dt, okay? So how do we solve this equation? Well, there's two ways. One is by series, if you're really good at series. I'm sure none of you are. And the second is by differential equations, where it's actually possible. Okay? The actual derivation of this stretches for like 3 pages, so I'll just give you the easy answer. If any of you want to see the results, I can show them to you and explain to you in person, but I mean, I'd be happy to, but you don't need to know for the purpose of this class. Yeah. But what's more important, though, is to understand what these numbers all mean. The integral, the second integral here. Okay, so if this is simply our linear, assuming no one dies, how much population is left? Well, not no one dies, but B does not change. So what is this? Well, this then would be this integral here would be the correction for how much of A did not die due to the fact that some parts of B died. So let's draw a picture to clarify that. This is A, and this is B. After time, after some time, this much of A dies. How much is that? Well, that's going to be alpha B times T, right? However, while that is happening, part of B also died. So, how do we account for the fact that, you know, during the time that these guys were dying, they were not shooting, okay? Dead guys did not shoot. So, there must be some correction to this death count to make up the real A of T. And that amount is our integral of second integral of alpha beta of A of T dt dt. Okay, so that's what's so important about this. Although this is like a scary formula, it's simply the correction on which the amount of this that did not die is not firing on that anymore. And that's also why this is a plus sign and not a minus sign. So the answer is, let's call this integral C. So C equals negative A naught plus alpha B naught T plus 1/2 A naught minus square root alpha over beta B naught e to the alpha beta T plus 1/2 alpha minus alpha plus alpha over beta B naught e to the negative alpha beta T. Okay? It's actually a very elegant formula equation, It's just a little burdened with constants. Yes.
Was this equation in the notes that you handed out?
This was not in the notes.
Okay.
It is in the green. It is in the green readers though. If any of you has the green copy of the reader, then it's in the back, and so is the derivation for that matter. So you only memorize this, but we do need to discuss where these variables go. Okay. So we can see that the correction depends a lot on alpha over beta. Okay, this rate is it actually goes up. Alpha beta times t, square root of that, actually goes up as the death rates for each side go up. So let's just bring some examples for now. Alpha over beta, where alpha is the death rate of A and beta is the death rate of B. So if alpha is much, much greater than B, so for the case that alpha is greater than beta, it means that that population B is killing population A at a rate much, much faster. Okay? So B is killing A much faster, which means not much of B is dying. Okay, if not much of B is dying, then that means that the correction is not going to be very much. And I guess this term, actually for long periods of time, we can actually ignore the second term here because it's to negative alpha beta t, and this is just 0 for long periods of t. So we can actually ignore that. So the main formula is right here. Okay, and so basically we have population B, this initial condition. And so we have a comparison of these two initial conditions multiplied by how much of alpha is over beta, so how much more alpha is over beta, multiplied by e to the alpha beta t. What this means is as time goes on, this effect is going to get greater and greater. If we have t approximately equal to 0, then we'll know, and then we'll see that the correction is virtually 0 because this alpha, this A and this A cancel. This alpha beta and this alpha beta together cancel out to be alpha beta t. Okay. So essentially what happens is for very short periods of time, this does not matter. For long periods of time, this matters more and more. In fact, to the exponent. Okay. So if you get nothing else out of this, you get the fact that if you are expecting a long battle, then the fact that so this correction starts mattering a lot. You can predict how much of your army you expect to have left. Okay, let's take a different case. What if your population A naught, is much, much greater than B naught? Well, if this is the case, then we go back to this equation, B naught minus beta A, and this will mean that the battle is over very quickly. So if your population is much, much greater, then the battle is going to be over before this e to the alpha beta t takes effect. So we see that this is not at all linear. This means that the longer battle stages, the more the correction has to be. And for a short period of time, we can actually just use for a short battle, we can actually use this equation and have it be fairly accurate. So these are things you can take into consideration when you're playing. You can say, oh, there's going to be a long battle. It's going to be like all my army against all their army, and it's going to take like 40 seconds. Okay, talking about time scales, 40 seconds is actually quite a long time scale for this T. A short T might be something like 1 or 3 seconds. A medium T would be something like 10 to 20 seconds, and 40 seconds is a huge battle. Okay, so you can take that into consideration. If you know how long the battle is going to last, you can see how important it is to have all of your army together. If all your army is together, then your A is going to be very big. A minus integral of alpha. If your A is very big, B minus beta, integral beta alpha beta times A is going to be it's going to reach 0 very, very quickly, and so this T is going to be very small. T is going to be small. This term simply goes away. There's no correction. Like in a long battle, well, we've already been through this. So you see the point. So that is population dynamics in as few words as I can put it. Again, if you want the exact derivation and all the limitations, like which constants have to be greater than 0, and how to model in like reinforcements, how to model in storm, how to model in plague swarm, lurkers, you should come speak to me about that, because that makes this equation tedious at best and impossible at worst. So this is all great, right? I mean, yay, we can do math. Everyone loves math. But without without experimental results, there's no point in doing all this. So let's see experimental verification of this. I'm gonna see woo for yeah. Woo math. Yeah, I like to hear it. And no, this is not a boxer appreciation course. We have here a very simple situation. Let's not worry about how we get here, because we're going to discuss build orders and timing and macro in the future. But let's assume the situation happened. This is a population of Marines. This is a population of a second group of Marines. Okay? Just like our N1 and N2. It's very simplistic. I love it.
Is this Boxer or is it someone else?
This is, I don't remember who this is. Them guys. I don't know who this is. But I do remember that these guys are pros. And frankly, Marine micro at this level is fairly simple and can be executed by almost anyone. Which means that all that matters is whether or not these people are paying attention. So if you are paying attention to this battle, your micro will be good. If you're not paying attention, it's not. And again, remember that micro at this scale matters at the order of times squared. So you can decide whether or not you want to concentrate on this attack, or whether you want to concentrate on the economy, which is exponent, for instance, which is to the time exponent. So here we see these guys not firing, not engaging just yet. Almost. Come on, Okay. So we see both sides executed a good micro. Both sides got off a single full kill, and then so our volleys are the same side. And then we see that N1 equals N2 times damage divided by hits, and then N1 also equals N2 also equals N1 times damage divided by HP. So right now we see we see a second volley, and this was not good enough micro because this guy did not die. However, this guy, did you guys see it? That the guy up there, the guy there, and the guy here all had bullet shots on them, but none of them died. Okay? This is a replay. We can't just go back and see it again. But the important thing is the damage from these guys was spread out through all those Marines, while the damage from those Marines on these guys were all concentrated on one guy. That one right here. All right? So that is the important thing. You realize that when damage is focused, this happens. Now the thing is, like, what's so important about a Marine? I mean, it's a Marine. It's 50 minerals. How about another one? You know. But the important thing here is that for the next engagement, for the next volley, so to speak, in our calculations, this N1 will have 5 Marines times damage, while Teal will only have 3 Marines times damage. So that's the important thing here. I mean, obviously there's so many other factors at stake, like the fact that there's going to be a vulture out momentarily, and vultures make mincemeat out of these Marines anyway. So don't get too hung up on the fact that guys lost a Marine. But the important thing is, micro does matter in some cases. Okay. So, and next we're going to see the importance of keeping your army together. This is the effect of your population dynamics. So let's assume, for instance, that population B was half of population A. Well, in that case, then population A will make mincemeat out of population B, and then during that time, A will kill B so fast that B won't have time to kill any of A. Yeah, these guys you all know. So we see here. This is a mod. obviously. Just a moment, let me find the sound. Because the commentator is low, right?
Yeah.
Didn't you make it a high quality?
Yeah.
The video still
That's
That's a lot of like lots of stuff.
just a moment, let me find the sound.
Take down the spiral
Excellent. These are the stasis fields. Okay? So basically the stasis field stasis this many units. This many units looks like to be about 30, 15, 20 supply or so? 20 supply, I would say. But the important thing is, I think these two are arbiters. So these two arbiters did not get a chance to stasis these guys. So the most important thing is, this population got cut in half, while this population did not get cut in half. And during this time, this population has free reign over these guys, as we shall see.
These cases are a lot of Stork's units, and these will also catch Stork's arbiter in the stasis field. This is horrible for Stork. Stork can use trouble here. But these might be able to win the game here. Stork goes up for all of Stork's units. Stork is losing this battle. Stork in trouble. Half of Stork's forces are in the stasis field. The rest of his forces are dying. Beast is going to be able to surround Stork's forces and kill them off now. This is going to be GG, guys. This is
going to be easy.
So we see, in a game that's like 40 minutes long, what it all depended on was the fact that half the army was not there. Half the army was not ready for combat when the time arose. Okay, you guys can see this game in the future. Oh, this is an amazing game. It has so many elements like micro, harass, timing. We'll see this game like a lot in the future. This is part of the same game, and we can see another part where having your army together really matters.
wish for a final force in this. Both players jockeying for position in the middle of the map, maneuvering around, trying to get a better position to affect the attack, and trying to storm the other players' army while not getting stormed themselves, trying to hold those choke points, and trying to gain control of the map. And it looks like the forces are going to clash here in the middle of the map. Storm goes over a lot of pieces. Storm goes over. These are the high advantage on that round, and that's going to be a little bit of a disadvantage for Storm. It looks like Storm, these are unfortunately behind those. Behind.
See, the important thing wasn't how many, well, the important thing was how many storms they could get off. But the thing is, the fact that their storms are matching means that no one got an advantage, right? Their storms were matching. Both players got the same number of storms off. However, the important thing is that White did not have his army all in one place. These guys were left behind because they took some roundabout way and got lost on this map, okay? However, Yellow's forces were all concentrating in one place and pushing to the same spot at the same time. So that means that Yellow's forces all fought together, making its population very high, and White's population was comparatively lower. So we did our calculations earlier, and we proved that this battle would obviously end poorly for White, which it did. And not only that, the remaining forces can then take care of these guys easily. Because the first battle, he had numerical superiority, and that resulted in him taking fewer losses, and that results in the numerical superiority for the second battle, during which he will again take fewer losses. So that is why it's incredibly important to keep your guys' army together, and we have proved that mathematically. Okay. So we can go on, I guess, with some more. So any questions about either marine micro on this graph? I mean, on these calculations, or the population dynamics on the board at the back. Any questions?
Do you want to do this?
Yes.
Do you want to film? You're right next to him.
Oh, okay. The question was, how does n2 multiply by m? Okay. So,
What?
so how do you figure out how HP? Okay. So that's going to be the population at any time. If you just multiply the population, if you multiply the population by the number of volleys, then you'll get the total damage you'll deal. So what we'll have is the sum of from I equals 0, I equal 1, denoting the first volley, up to m, of n2 minus m times n1 d HP. Oh, sorry, I guess we have to multiply this by d, because this is how much damage it does. This is how many stay alive. So what we'll have here is, this is a constant, so it simply is m2 times m. Okay? And this, we have to, sorry, I keep doing this. It's different in my notes because the variables were different. I have my own notation. But in this, I gets added every single time. So this equals minus n1d over hp times sum of I equals 1 up to I equals m of I. And if you remember back to, I don't know what class, algebra 2, I guess, or something like that, the sum of I equals 1 to m of I equals, oh crap, equals m times m plus 1 over 2, okay? And we plug this back into here for I, we have this over 2. Sorry I made the mistake, but the important thing is, even with the 2 here, it's still of the second order. That's basically it. Anyone else? Yes.
For stuff like shield regeneration or healing,
Uh-huh.
is it easier to factor that with damage dealt or as a separate constant factor at the end?
Okay. How do we factor in regeneration into all this? Well, we have here, we simply denoted alpha as the death rate, right? But it can also be seen as the survival rate or replenishment or whatever. Or let's say we're fighting on a choke and the total amount of damage can only be so much. That also goes into alpha. So this constant right here, if you understand it completely, is very powerful in manipulating your equation. What will happen is rate of this population change is no longer just alpha b, okay? Let's take this in a very, very complicated fashion. What if there's shields? What if regeneration? This plus alpha, okay, so in this case, we'll have to make alpha be negative because this is a population change. So we'll have dA dt equals this because it's going down. Reinforcements come. Shields regenerate. Okay, let's say shields regenerate at some rate, right? At the regeneration rate, but only of the units that are still alive. Okay? What other factors can you guys think of? How about fighting at a choke? When fighting at a choke, absolute value of negative alpha b has to be less than some amount, where some amount is limited by the number of units that are fighting at one time. We'll get into a little bit more of this later on when we do with flux. But you can see that careful changing of this rate here, rate of change. Our simplistic model only covered deaths. If we covered any number of changes, reinforcements, regeneration, or fighting a choke or whatever, we can manipulate that rate to reflect anything we want. Yes.
Well, for most fights, is regeneration really feasible to include, or not feasible? Is it practical to include regeneration?
No, not really. So I mean, if you, I can't just say not really, right? I have to show it somehow. I mean, through many games, you'll start realizing that the regeneration rate isn't effective. However, if you simply plug it into the calculation, you realize that R is a tiny, tiny, tiny amount compared to damage dealt. So if R equals something like 1/100th of alpha, then that's how it factors into the equation. Okay? So, I mean, because like, let's say we have like Zerg regeneration compared to like Zergling damage or something. This alpha is, I mean, this R is literally going to be less than alpha over 100. Because Zerg regenerates, I think, 1 damage point every like 2 seconds or so. And Adrenaline like full upgrades does 8 times 3 damage per second. So that's something like 48 to 2. 48 to 1, actually. Okay. So actually, for Zergling on Zergling contact, we have R equals alpha over 48. If alpha was offset by something like Storm or Lurker Splash, then it's an enormous number compared to R. So you're right in saying that, in bringing that up. It's just that no one can say what the answer is going to be. But if they can show it, if they can prove it, then that becomes a good result. Of course, if any of you want to dispute this, you can either show me a calculation or show me experiment. In this experiment, we see that regeneration was very, very effective. And we'll say, oh, let's modify this a little bit. Because calculations always follow experiments. Okay. Very good question. Anything else? In that case, we can deal with concept of flux. Sorry I'm throwing so much math at you guys right now, but I mean, it's a really good way of modeling. And if you guys have better ways of modeling, like with computers where we're like having two AI fight each other, go for it and send me the replays, or send me like a list of 100, like if you run the experiment 100 times, it's great, show me the results. But I believe that calculations are an extremely valuable way of doing things. Yep?
How would you model something like even more complicated, like dragoons when they're kind of big and they don't have range upgrade? It's not possible to focus fire.
Well, that's the thing. If you can experimentally measure an alpha, then you can't calculate your alpha out. It's very difficult to calculate how much alpha will be based on damage and health and attack power or whatnot, but you can still measure experimentally. And that's going to be part of, actually, one of the homework questions. It's going to be how fast does an army die? Well, you can't really account for everything. I know that. You know that. You can't account for how well storm damages. You can't account for how well someone surrounds. But you can approximate it by running experiments 10, 15 times, watching 300 replays or whatnot. So we're going to deal with flux right now. We're going to define flux. We're going to define flux to be the total number of units that can attack at once, or the total number of units within attacking range. Mathematically represented, this is the integral of your against your damage. The integral of your damage as a function of the number of units you have, dA. Where A is the area from which they're firing. So let's say that let's say we have dragoons. Okay? These are all dragoons. I should probably use blue, huh? Because that would represent dragoons better. Sorry, that's the dragoons I see. Suppose they're all coming in and firing at some target. This is the target, okay? The back dragoons won't even get to damage, won't even get to the fight until something happens, until these guys die and they move up, or until they get range upgrade and they fire, or whatever. These guys won't even get to fire until they get there. So these guys are not counted in the DA. Let's take another example, for instance. Let's say we're fighting at a choke. So this is Luna, okay? There's our choke. Let's see. There's 3 zealots. Yeah? There's a horde of Zerglings right here. Okay? That's a horde, okay? And then this is the front line Zerglings. Okay? This is a crude description of 3 zealots holding choke. Okay? So what do we have here in terms of flux? Well, this part of the Zergling army is doing nothing but milling around, and being lost. This part is the part that's attacking. And this is what goes into integral of damage of all your units times area. So our flux can't be just that, because how will we normalize it? How will we compare it to anything else? So we divide it by the sum of all the damage of all your units. Okay, this is just very general terms. I mean, it's not very, again, you can't use this directly in any of your calculations, but this is basically the general form of things. We have the total amount of damage from the area that you can do, compared to all the damage you can do, period. Okay? So if all your units are attacking at once, you have 100% flux. If like a third of your units are attacking at once, you have a third. Your flux is 33%. And frankly, that's terrible. Okay? So how do we use this in practice? Okie dokie. So do you guys know, alright, who here thinks it's better to attack in a single file line heading straight for the army? I used to do that all the time, okay? Who thinks it's better to attack in a broad band, all against the army at once? Yeah, now I think that. So we have a model of this is your army, and the density is equal to lambda. Okay, the density of units along this arc is going to equal to lambda. This is your enemy. By the way, let's assume they have range. Okay, let's always assume these guys have range because when we're dealing with surface area. Okay, how much flux do you have? Oh, supposing that this distance d is less than r, where r is your range. How much flux do you have? 100%. Now let's see this. Okay, this is your army, and let's suppose this is your range. Okay, how much flux do you have? Well, 50? I'd say that's like 15. 0.15, you mean? 0.15, 15%. However, what's also important is to compare that to the flux your opponents have. How much flux do your opponents have? Okay, let's say that's going to be like 80%. So obviously your opponents have more flux, they're going to do more damage. Oh, that's just a general case. Now we can prove it. Oh, by the way, all these calculations are actually in your readers, the green versions at least. They're in the very back, and they're in the back here, and that's how they're different from the blue versions. So let's assume here that we have your opponent's army, your enemy army, right here. Okay? And then you are advancing like so. We're not going to advance in an arc because an arc is too hard to calculate. Let's just advance in a straight line, in a broad line, let's say. Okay? And let's assume you all have the same range. Okay? So, in these calculations, how much flux do you have versus how much flux they have? Well, obviously, when you're far away, if you're right here, neither of you have any flux. So as you move closer, we can calculate how much your flux increases compared to how much their flux increases. So we'll have the following equation. So let's suppose V equals dx dt, where V is the rate at which you advance. So obviously x will equal vt. Y, okay, and y here is how much of your army is going to be capable of firing. Y equals square root of 2r minus 2rx minus x squared. I don't really think you guys want to see the derivation. If you guys want to see the derivation, again, see me after class or see me during lab or flip through your book. Okay. Essentially, what we have here is your enemy's rate of flux increase d phi dt is going to be lambda v, because it makes sense, right? As you move more and more of your army into their range, they're going to have, well, lambda times v, whatever v might be, of their army attacking, and of course this divide by total amount of army they have total. Your rate of d phi dt is going to be r minus x over 2rx minus x squared lambda v. And it can be shown that this, well, of course, over total army again. This number is greater than this number for this number is greater than this number until you get past the midway point. So if your range is D, then everywhere until you get, so when your distance between them is D over 2, when the distance between your army and their army get to D over 2, that's when your rate of flux increase starts decreasing compared to his. But that's never going to happen because as you're fighting in a line like this, as you're fighting in a broad line like this, their frontmost guys are always going to be dying. So this distance over 2, you're never going to reach this D over 2. I mean, you might if they have like, very buff units and you have weak units, but that's again subject to change, and you have to think of a better way to fight if you're fighting units that strong. So the point is, once you get once your distance between you guys gets to D over 2, then your rate of flux will start decreasing compared to their rate of flux increase. However, their frontline guys are going to be done. Okay. Okay, you guys have done enough math for today, so the rest of the class it's going to be no math whatsoever. However, before we take a break though, if you guys could get since this is the first time this class is offered, if you guys could give me like an assessment on like how. So if you guys could get out a piece of paper and write down the following. One is where you see the class going. Where you see the class going, and is it somewhere you want to see it go? Okay. First thing is where you see the class going, and where you want to see it go. Second thing is more theory, or more calculations. And 3. I guess speaking lecture style. So like you can say like, you walking around really distracts me, and it hurts my eyes when you blink. Okay, I'll just have to stop blinking. So I want you guys to comment on where you see the class is going and whether you like where it's going. Second is more theory or more calculations. And third is speaking lecture style. All right, the class will start again in 10 minutes, and if you guys can have these things done by the end of that time, that'd be great. Gas, I guess. Units. And let's just keep it at that. Minerals, buildings, and units, because you can't really attack their energy. I mean, I guess you can EMP them, but that's minor compared to everything else. So what do you hit out of all of these? And why would you hit it? If you hit something like minerals and gas, if you hit their economy, for instance, will it fight back? No. If you hit their buildings, will it fight back? No. Alright. Turrets, I guess. Okay, but granted, I guess you can count like turrets and cannons or whatnot in their. But if you attack a supply depot, it won't hit you back. Okay. How are their units? Will their units fight back? What? Yes? No?
Yeah.
Sort of. So we have lots of units and some units. Okay? That's just a rough way of saying if their army is together or not together. But suppose you catch an isolated 10 supply group with your army, with your 50 supply army. Doing the calculations we did before, will the sum army do anything to you? No, because the battle will be over so fast that you can kill them with very little damage to you. Whereas if you try to take on their entire army, what happens? They'll fight you, they'll damage you, you'll damage them, and we'll go through all sorts of calculations. We find out you take damage. So I think the thing I want to impress on everyone right now is the importance of attacking what does not fight back. You have to attack what does not fight back. Why is that? Well, if you're attacking their economy, let's say you attack a nexus or a probe or a command center or a drone or whatnot, if you attack that, then you're reducing their their resource intake. You're reducing the rate at which they increase resources. If you attack their army, you're not reducing their rate of resource intake at all. If you attack their buildings, take out 8 supply depots or whatnot, you're reducing the rate at which they can build more units. So you're reducing the transformation resources. So basically the point is, you can get something for nothing. And why attack something that can hit you back when you can get something for nothing? I mean, obviously, under most cases, you won't be able to get a straight path to their supply depots or their pylons or overlords or whatnot. So you have to engage their army at some time. But even then, you don't have to attack their whole army at once. I mean, if you can, since you have this great quote that if you outnumber him 10 to 1, attack him. If you outnumber him 5 to 1, strategize against him. If you outnumber him 2 to 1, build up your forces more. If you fight him 1-on-1, you will lose. If you fight him 1-on-2, then divide him. If you fight him 1-on-5, then defend. If you fight him 1-on-10, run away. Okay? Each of these, if you think about it, each of these is built around to fight where he cannot hit you. Because if you run away, you preserve your forces. He can't hit you, and if you fought, you deal minimal damage to them. If you don't fight, he can't do any damage to you. If you defend against them, you use your better terrain, use your better micro, you use choke points or whatnot to make sure he does the least amount of damage possible. All the while, when you have your overwhelming advantage, you can fight him. So for like Tyler's Hydras, he just simply attacked him like he wasn't. When he dropped those, I guess 10, 12 Hydras, and like 15 lanes or so into Terran space, were they getting hit by anything? No. They were fighting something that could not fight back. Whereas you saw exactly what happened when he used all of his army to engage the Terran army. What happened? Splash, splash, splash. You see dead Hydras everywhere. Okay? So, I mean, in a purely theoretical point of view, you should always attack something that does not fight back. However, that can't always be the case. So if you can't always fight what can't fight back, then you have to choose your battles correctly. I mean, we went through some of the calculations of how to choose your battles, because you always want to choose a battle that you can win. Sun Tzu also said that a smart man will win his battle first and then go for the fight, whereas a losing army will fight first and then seek its victory. What basically he's saying is you have to make sure you're going to win before you make the fight. So when you have everything scouted out, when you have your flank set up, and then you know you have advantage, that's when you push it. So like Tyler said, you take your advantage and you push it. If you don't have advantage, you just run away. So I mean, we'll go over this in more detail next time since we're kind of limited on time. But basically, the point of your army is to increase your economy while decreasing theirs, increase your production while decreasing theirs, and decrease their army while increasing your own. Take the position of battleground and you await your enemy at ease. One who takes position later at the battleground hastens to do battle is at labor. And thus one skilled at battle summons others, not summoned by them. In other words, fight where it's most advantage. So the final, I can't. Alright, there's the final equation. P vector plus your delta P as the result of your choices has to be greater than or equal to your opponent's observed vector plus the uncertainty in what they might have plus the effect until the last time you saw them. So you have to